Hi, welcome to me313 Mechanical Engineering and Thermodynamics. The topic of this video is the Otto cycle, and the section in the textbook is section 9.5. Here are the learning outcomes. At the end of this video, you should understand the relationship between an actual and an ideal Otto cycle. You should be able to derive the Otto cycle efficiency using the cold air standard assumption, and you should also be able to calculate the properties for all four states of the ideal Otto cycle. So first I want to go ahead and discuss the ideal Otto cycle. And so remember, ideal cycles we have are these discrete steps that we go through where it comes to complete stop each time. And so here I'm showing the ideal Otto cycle on the bottom. And so we initially have, here's our piston inside our cylinder. And it's initially at a larger volume and it goes ahead and gets compressed. So we'll go ahead and call this state 1. And it's got a relatively large volume and low pressure. So I'm going to put that point right there and say that that's point 1 on a PV diagram. Then the first step is compression, and so the piston goes upward as it's drawn on the diagram here to a smaller volume, and the pressure increases. And so on a PV diagram, we would go up and to the left, and there would be point 2. Then what happens is the spark ignites a fuel mixture, which causes the temperature to go up, and so what ends up happening then is the temperature increases very dramatically, and we go up to point 3, where we're at the same volume, but we're at a higher pressure. Then what we end up with is what's called the power stroke. The piston moves downward, and it moves down into this direction, point 4, and we go ahead, and then exhaust begins, and the exhaust valve opens, and we complete the cycle, and we return to point 1. So we can think of this step here as this is where heat is added to the system, because by the fuel igniting it heats it up, and then this is the exhaust step, and so that right there is Q out, that is heat leaving the system. And we can draw the same thing on a TS diagram, which is pretty helpful. So let's go ahead and we're going to start off at point 1. Well, point 1 we have a relatively low temperature and a relatively low entropy, so I'll put point 1 right there. We have the compression step 1 to 2, and if this is an ideal cycle, it's internally reversible. It's going to be isentropic, and so it's going to go straight up, and so there would be point 2. Then we have the heat addition step, which causes the temperature to increase and also the entropy to increase, and so it will go up and to the right, and there would be point 3. And then we have the power stroke where it expands. If there's no friction, it's internally reversible. It's going to go straight down, so then point 4 will be straight down from there. And then we lose energy. Heat is released during the exhaust step, and we go back to our initial volume and our initial state. So this right there is the Q out step, and this step up here is the Q in. Very helpful to recognize both the PV diagrams and the TS diagrams. And also remember the area inside here is the network on both that diagram and this diagram. So the area on both of those is the same. So let's go ahead and derive an equation for the thermal efficiency, and we're going to use the cold air standard assumptions that we discussed in the previous video. So first of all, remember that the thermal efficiency is the network of the cycle normalized by the amount of heat that I put in, and I can go ahead and write that in terms of the Q out and the Q in, 1 minus Q out over Q in, and now I'm going to use little q's just in terms of per mass. So I can go ahead and divide through the mass each time. Right. So first of all, I want to get equations for Q out and Q in, and so if I go back to my previous cycle here and look, Q in is steps 2 to 3, and Q out is steps 4 to 1. And so I can actually know that the heat going in is going to end up being equal to CV times, this will be T3 minus T2, right? Because what that is this is equal to, sorry, that's T3 minus T2. That's U3 minus U2, that's the internal energy. And we can also write in another equation for Q out, which will be CV, and this is going to end up being equal to T4 minus T1, because that was equal to U4 minus U1. Right? So I can go ahead and put those into this equation. Now, the cold air standard assumption assumed that we had an ideal gas with a constant heat capacity, and that's why I'm able to do these CV substitutions here for the internal energy terms. Right? So now if I go ahead and put that in, my CV terms are going to go ahead and cancel, and then with a kind of a simple equation where this is going to be equal to 1 minus, this is going to be T4 minus T1 normalized by T3 minus T2. And then I'm going to do a little bit of algebraic rearrangement, and the book shows this as well. But what I'm going to do is I'm going to go ahead and move my T1 and my T2s out of here. So I end up with T1, and I'm going to have T4 over T1 minus 1. It's just a little bit of algebra here. I'm going to go ahead and bring out T2, and I have T3 over T2 minus 1. And the reason that I'm going to go ahead and do this is that if you remember the steps that are going from 4 to 1 and 2 to 3, right? So 2 to 3 and 4, I'm sorry, 1 to 2, sorry. If you look at steps 1 to 2 and 3 to 4, those right over there are isentropic steps. And so I know that I can do things like go ahead and say that, you know, for example, T4 over T3 is going to be equal to V3 over V4 to the k minus 1. That would be an isentropic relation that we had, if you remember back from chapter 7 of the book. And so if I go ahead and do the same thing with 2 and 1, I can end up rearranging this equation to a much, much simpler equation. And this becomes 1 minus 1 over, and it's going to be r to the k minus 1, where r is what we call the compression ratio. For example, it would be V1 over V4, and that would be the same thing as, V1 over V2, which would be the same thing as V4 over V3. And so this right over here is the difference in the volume. So if we come back to our, actually I can go on the previous diagram and show you, right? So I'm looking at this volume right over here divided by this volume right there. So that's the compression ratio of the cycle. And so I have a pretty simple equation here in terms of R. And so that's right there what the thermal efficiency is. Now that equation only works for the cold air standard assumption where I had these constant heat capacities and ideal gas assumptions. But it gives me a pretty good representation of what the thermal efficiency would be for the Otto cycle. Just a couple of qualitative things about the compression ratio. Here we've got a plot from the book of the compression ratio R, and this is what the efficiency is. And one of the things we realize is that the compression ratio, as the compression ratio increases, the thermal efficiency increases. So what that says is you want to run at high compression ratios. And in fact, this diagram here, somewhere between about 8 and 11 is typical for Otto engines that are running. And so you can end up having theoretical efficiencies. Again, these are theoretical efficiencies, on the order of 50 or 60%. Now you may wonder, why don't you go to even higher compression ratios? There's a couple reasons. One, you kind of got the law of diminishing returns here, so you don't get a whole lot of advantage by running the higher compression ratios. You end up with much higher temperatures, and the other problem you have is engine knock. You get pre-ignition inside the cylinder, which you don't want. And so that usually restricts our compression ratios in Otto engines currently at around 10 or 11. You can go ahead and increase the octane of your fuel, and you're able to go ahead and increase that a little bit. Some race engines are able to do that. But in general, this is what we'll see in most cars that we have. A couple other kind of qualitative relations. This again is a plot of the efficiency as a function of compression ratio. And these lines over here are for different values of K. Now remember, K is the ratio of the heat capacities of CV over CV. And so this would be like, for example, K of 1.3. This would be 1.4, which would be typical there. This line up here, I think, is about 1.667, which is typical of helium. So what we realize is that if we were to go ahead and actually use things other than air materials that have larger values of K, we could go ahead and get a higher efficiency for a particular compression ratio. Now, with engines, we tend to go ahead and use air just because it's pretty free, easy to get. It would be difficult to go ahead or more expensive to be running Otto engines that are using helium, and simply to go ahead and increase our efficiency. But in theory, it could be done. All right, so what I want to do next is just go through an example where we're going to go ahead and solve for all the states in the Otto cycle. So here's the problem we're going to look at. We have an Otto cycle. We'll do an ideal Otto cycle. Has a compression ratio of 8. We're told what the inlet conditions are. So this is the air that goes into the engine. It's 100 kPa atmospheric pressure and 17 degrees Celsius. The other thing we're told is the amount of heat that is added. And so we're told on a per mass basis, 800 kilojoules per kilogram. And what we're going to do is we're going to solve for all 4 states, know all the conditions, and then we'll determine what the thermal efficiency is. So the first thing I like to do when I solve these problems is draw out both the PV diagram and the TS diagram. So let's go ahead and draw the PV diagram first. And remember, it looks like this for the Otto cycle. This would be point 1, 2, 3, and 4. And then we'll draw the TS diagram as well. And it looks like that for the ideal cycle. This is point 1, 2, 3, and 4. All right. So first thing we're going to do is we know the initial conditions. This is 0.1. That's the inlet to the engine. It's 100 kPa and 17. So we know 0.1. And to solve these problems, we're just going to go ahead and move through the cycle step by step. So we're going to go from 0.1 to 0.2. So going from 0.1 to 0.2, this right over here, remember, this is the isentropic compression. You can see it's isentropic. It's straight up and down on the TS diagram. And so I want to go and figure out what conditions 2 are relative to 0.1. And I know one thing over here is that since the compression ratio is 8, the volume at 0.1 is 8 times that volume at 0.2. And the other thing I know at 0.1 is the temperature is 17 degrees Celsius, or at 290 Kelvin. And we'll realize in a second why it's nice to have that in absolute. Because if you remember, there's a relation, an isentropic relation that says, for example, that T2 over T1 is going to be equal to V1 over V2 to the K minus 1. Right? That was the isentropic relation between two different states, and this is an isentropic compression. And so V1 over V2 is simply 8, so it's 8 to the K minus 1, and T1 we just saw over here is 290. So from there I can go ahead and just directly solve that equation for T2, and I'll find that T2 is 666 Kelvin. So now I know everything at 0.2. I know the temperature at T at 0.2, and I know the volume. The volume is 1/8 at the initial. So now we're just going to go ahead and keep working our way through the cycle. Now we're going to go from 2 to 3. Remember, 2 to 3, that's the heat addition step. So there's Qin. And so I can go ahead and write a first law equation that says Qin is going to be equal to U3 minus U2, or an ideal gas, it's going to be CD T3 minus T2. Right? And I know T2 at 666. I know Qin, that's equal to 800 kilojoules per kilogram. So now let's just go ahead and directly solve that equation for T3. And I can find out what T3 is, and that is 1780 Kelvin. So there's the temperature at the end of the heat addition step. That point right there, and that point right there. We're almost done. We're at 0.3. We just need to go ahead and go down to 0.4. So let's go ahead and do that. So what I'm going to do is actually, I'm just going to kind of leave my diagram up here. Go ahead and just erase some of the work that we've done here so far. There's my eraser. Oh, well, let's just go to the next page then. There we go. All right. So what we've got, I'm going to go ahead and just sketch up my PV and my TS diagram again, just to remember what they look like. 1, 2, 3, 4. 1, 2, 3, 4. PV, and there we go ahead and we have TS. All right. So we were at 0.3, and we just wanted to get down to 0.4. And so this is my power stroke. 3 to 4 is isentropic. So we're going to do the same thing we did when we went from 1 to 2. We're going to do an isentropic relation. T3 over T4 is going to be equal to V4 V1 to the K minus 1. 4 over 1, that's our compression ratio. That is 8 to the K minus 1. We knew what T3 was, so now let's just go ahead and directly solve that equation for T4. So plugging in those numbers for T4, and I find that T4 is 775 Kelvin. All right, so now we're at 0.4. The last thing is to solve this step where we've got 4 to 1, which is the heat rejection, give us Q out. And so we can go ahead and solve now for what Q out is, because we know T4 and T1, because T1, remember, was 290 Kelvin. T4 is 775. So let's go ahead and solve for Q out, and I can find out that Q out is CV T4 minus T1, and if we plug those numbers in there, that becomes 348 kilojoules per kilogram. All right? So now I know Q out. Qin was given in the problem. I can go ahead and just calculate what the thermal efficiency is. 1 minus Q out, or 348, and divide that by 800. And that's going to give me my thermal efficiency of 0.565, or right, 56.5%. All right, kind of similar to what we saw in that diagram for what are typical thermal efficiencies for auto cycles, auto cycles. All right. So what I want to do now is I'm going to solve the same problem, but what we're going to go ahead and use is we're going to use a variable heat capacity, a variable CP, variable CV. The reason we're going to do that is we actually saw what that high temperature was. It's 17 so Kelvin was pretty high. We went up over 1,000 degrees, about 1,500 degrees. a pretty large change, and so it's probably good to account for this variable heat capacity. So I'm going to solve the same problem that we just did, but we're going to go ahead and use a variable heat capacity. So we'll be able to go a little quicker because we're solving the same problem, but there's just going to be a couple steps that are a little bit different. So again, I'm going to go ahead and draw up my cycle. Doesn't hurt to keep drawing these pretty often because then you'll know how to do them quickly on an exam. 1, 2, 3, 4. 1, 2, 3, 4. All right. So remember, we know point 1, that's 290 Kelvin, right there, and we want to go ahead and get to point 2, 1 to 2. Okay? But since we're using a variable heat capacity, we can't use that simple relation that we used before. We need to account for this. And the way that we can do this, remember that V1 over V2, compression ratio of 8. Remember the relative volume. There was that thing VR1 over VR2. Those were the relative volume. These were functions of temperature. And so you can look those up on a table, like on table A17. And so we can look up what it is for VR1, which is going to be at 290 Kelvin. Find out what is the value of VR2, V sub R2, and then we can find out the corresponding temperature. Let's go ahead and do that. What we need to do is go to our tables. So here's our tables, and what I need to do is scroll down to A17. There we go. So there's A17. Go ahead and there we go. All right. So here's table A17, and so what we see is there's values at a particular temperature. Here's my value of V sub R. So for example, if I wanted to know what it was at 290, I see VR is 676.1. So if I come back to my problem here, that is going to be, oops, where did my pen go? 676.1. And that is equal to 8, right? So that's going to be over VR2. Sorry, this ratio is equal to 8. And so from there, what I'm going to do is I'm going to figure out what is VR2. So I solve for VR2 with that equation. VR2 is 84.5. And then what I need to do is return to my tables, and I need to figure out where that is. And 84.5 is somewhere here between 650 and 660. So I'm going to go ahead and interpolate a value to find out what that is. And if you do that interpolation, you find out that, oh gosh, I keep using my pen, excuse me. I find out that T2 is equal to 652 Kelvin, right? So going from 1 to 2 was a little different. Again, we were using an isentropic relation, but a little bit different isentropic relation. All right, so let's keep going. Now we're going to go ahead and go to 2 to 3, and going 2 to 3, well, this is our heat addition step. So Qin, which is going to be equal to U3 minus U2. I don't want to use a constant heat capacity, so what I'm going to do is I need to look up my values of U2 and U3. So again, I'm going to go to the tables, and we're going to look up our value of U2. So remember, we were looking at a temperature that was around 652, and we're going to have a value of U2 that's going to be somewhere between this 473 and this 481. And so we're going to interpolate a value for that. And so what I have, again, is determined that U2 by interpolation is equal to 475.11 kilojoules per kilogram, interpolating that off of the table. And so now I'm going to go ahead and solve for U3. So U3, which is going to be equal to U2 plus Qn from that equation right there. And I go ahead and find out that U3 is equal to 1275.11 kilojoules per kilogram. And then I can go ahead and find a corresponding temperature as well if I want to know what T3 is. Again, just interpolating off the table, T3 is 1575 Kelvin. All right. So now we're going to go ahead and we want to go from 3 to 4. Going from 3 to 4. And again, we're using this isentropic relation with a variable heat capacity, the V4 over V3, which is equal to the compression ratio, is equal to VR4 over VR3, the relative volume. Here's T3, 1575. I can go ahead and find a corresponding value of what VR3 is off the table A17. What they get, that is 6.1. So I can go ahead and plug that in there, find out what is VR4. And so VR4 is going to end up being equal to Let me find it there. Oh, I don't have it. Actually, what I've got is my corresponding temperature. T4, and T4 is 796 Kelvin. Right, so then we got our final point. Is point 4. At this temperature there, I can find out what is U4. U4 is 206.91. And that is kilojoules per kilogram. And now I'm pretty much done. Now I just need to go ahead and determine what my thermal efficiency is. So thermal efficiency, 1 minus Q out over Q in. And that's going to be 1 minus, this is now going to be U4 minus U1. That's the heat that left the system over U3 minus U2. And if I look up all of those values, I get a thermal efficiency of 0.52 or 52%. Okay. So contrast that to the other one, which had 56%, so about 4% different. Not dramatic, but I'll tell you what, in terms of engine designers these days, they care a lot about 4%. And so this is going to give us a much more accurate answer, a little bit more work, a whole lot of looking up values in A17 and interpolating the values. But other than that, it's pretty straightforward.